Jupiter's by far the largest planet in the solar system. It has an influence on everything else. So if we want to understand how do planets form, how do solar systems form, we really have to start with Jupiter.
By studying Jupiter, you're going to get one piece of the puzzle, not necessarily how life formed, but maybe how the ingredients that made up life eventually got spread around in the early solar system and got to us.
We care about the light elements because that's what we're made out of. We've got a puzzle about where these volatile elements, these lightweight elements like nitrogen, carbon, noble gases, where they came from.
To determine how much water is in Jupiter is essential to understand how this planet came to form and then how it influenced the formation of all the other planets in the system.
When the Earth formed, in the absence of Jupiter, it probably would have gathered very little water and organic molecules, which would have been concentrated in the colder outer part of the solar system. What Jupiter evidently did as it formed was to scatter cold material that contained water ice and organic materials to the inner solar system, where it could be captured by the Earth and the other terrestrial planets.
We learn about the origin of the solar system, we're learning about our own origins, we're learning about how life comes to be, about who we are and what our place is in the universe. It's about knowledge and about humanity's quest to understand.
Jupiter is a gaseous planet, hydrogen, helium. There is no magnetized crust that obscures our view of the dynamo deep below. So the exciting part about the Jupiter mission is that we'll be able to image for the first time the magnetic field on the dynamo surface in a way that would never ever be possible on Earth. Jupiter is also the planet with the largest magnetic field. Its magnetosphere is huge. If you were to look up into the night sky, and if you could see the outline of its magnetosphere, which you can't, it would be about the size of the moon in the sky. It's a very, very large magnetosphere. In fact, in the Voyager program, we learned that the magnetic tail, the part of the magnetosphere that is drawn away from the sun, extends all the way out to the orbit of Saturn and in all likelihood beyond. It's a very large feature in our solar system. It's a pity we can't see it.
Weather on Jupiter is confined to a rather thin layer, kind of high up in the atmosphere. So the tops of the clouds are what we're seeing when we look at Jupiter. One thing we're seeing in the southern part of the equatorial region is little V-shaped clouds or chevrons, and we wanted to understand how those are moving in the atmosphere.
What we think chevrons are simply holes in the clouds. They're simply areas where we don't see any bright white clouds.
The Cassini mission flew by Jupiter in the year 2000, and because it was a slow, distant flyby, we got a lot of coverage of the planet over a long time period. So we were able to put those images together and make movies. What we found by looking at the movies is that they're not just moving from east to west, they're moving up and down, tracing out what's called a Rossby wave. We have these on Earth as well. In particular, we see them around the poles, there's circumpolar jets, and we can also see them in the jet streams at mid-latitudes.
Jet streams on Earth typically flow from west to east, but sometimes you can see them meandering from north to south, and that's a signature of Rossby waves here on Earth. These meanders can sometimes grow stronger, and that can lead to everyday weather changes, such as the passage of fronts or storms being generated.
For most people, what we really want to understand is weather on Earth, and what are the things that affect weather on Earth. Now, Jupiter and Earth are very different planets. We don't have land and we don't have seasons on Jupiter. On the other hand, we see very similar weather phenomena. So being able to understand and study another planet teaches a lot more about what's common in an atmosphere on the Earth.
So when we look at Jupiter, we see a lot of structure that looks very similar to the Earth. We can see storms, we see cyclones, we see anticyclones, and these sort of storms and weather systems that we see on Earth are very similar and they're happening on Jupiter. Fluid mechanics is hopefully the same everywhere in the universe, but Jupiter and Earth are very different. Jupiter is much bigger, it rotates a lot faster, they're made of different material, and Jupiter's much further away from the Sun than the Earth is. The quasi-biennial oscillation, or the QBO, on Earth is an equatorial phenomenon in the stratosphere where the winds are changing direction approximately every 2 years. Depending on which phase the QBO is in, eastward or westward, the temperature signal corresponds to that. So it's warmer in the eastward phase and cooler in the westward phase. It's been shown that it can actually be a barrier to transport of aerosols across the equator and has been linked to the frequency and the formation of hurricanes in the Atlantic and the Pacific Ocean. The long-term scales on Earth's climate is something that we're very interested in, and how that applies to other planets' atmospheres is really why we're studying Earth and Jupiter. The quasi-quadrennial oscillation in Jupiter's stratosphere is a temperature signal that we see in the equator, where we see the temperature get warmer and cooler approximately every 4 Earth years. We used a general circulation model where we focused on simulating the effects of small-scale waves produced from convection in Jupiter's equatorial region to simulate the QQO. The waves propagate upwards from the clouds and force the winds in the stratosphere to change direction, going from eastward to westward approximately every 4 years. Our model was able to reproduce the behavior of the QQO, but was also able to reproduce temperatures from the observations, and both of those together give us a lot of confidence that our model is very accurate in what's driving the QQO. The outer planets serve as a laboratory for understanding atmospheric physics under very different conditions that are present on the Earth. Understanding how their atmospheres change and evolve and their climates can give us insight into any planetary atmosphere.
When we look at Jupiter, we're seeing the top of its atmosphere and its weather layer. And its weather layer contains a lot of interesting features such as jet streams, vortices, storms, and these particular features called hotspots. So hotspots are like holes in the clouds because they appear very dark when observed in visible light, but in near-infrared light they appear very bright. This indicates that we're seeing deeper down into warmer layers of the atmosphere. Hotspots have been previously studied by the Galileo atmospheric probe. In 1995, the spacecraft released a probe that descended into Jupiter's atmosphere, specifically at a hotspot. And this probe made the first in situ measurements and the only in situ measurements of Jupiter that exist today. So it's very important to understand how hotspot meteorology works in order to place these in situ measurements from the Galileo probe in its proper context. In 2000, the Cassini spacecraft flew past Jupiter and created a series of still images that we compiled into time-lapse movies of Jupiter's atmosphere. Using these movies, we observed Rossby waves that caused north-south meanders in a jet stream south of the equator. With new movies, we instead focused on hotspots. Hotspots are unique because we believe that there is a Rossby wave similar to what we previously detected, but instead of this Rossby wave moving north-south, it primarily moves up and down in the atmosphere. The downward portion of the wave pushes air down into warmer layers of the atmosphere. This causes any clouds that are embedded within the wave to evaporate and prevents further clouds from forming. So at any given time, there are approximately 8 to 10 hotspots in Jupiter's atmosphere that are spaced roughly evenly apart from one another. We believe that each of the downward portions of this Rossby wave corresponds to the hotspots that we see on Jupiter. This new finding is exciting because it will allow us to re-examine the Galileo probe data and allow us to better understand it and better place it in the context of Jupiter's overall global climate and atmosphere.